So the last class we were focusing on the product rule and the quotient rule. You had some homework. Any questions? Number 5. I will. Okay, number 5. You're given 1 over y squared minus 3 over y to the 4th, all of that times y plus 5y to the 3rd. Now, I should first point out, it's capital F of y. They want you to take the derivative of this, right? And here, y is our variable, so y is like x would be. Let's make sure we're all okay with that. Capital F is the name of the function. So what we're looking for here is capital F prime. You could just expand this out, you know, this times this times this times this times this, figure out what it is, and then just do power rule on each one. But since this is the section on product rule and quotient rule, I'm going to do it using the product rule. So before I apply the product rule, I recognize that we do have a product. That's F, that's G, right? And so our derivative, capital F prime of y, should be equal to F prime G plus G prime F, right? So let's take a look at F. Are you going to be able to take the derivative of this? Yes, but you're going to need to rewrite these as powers of y. So maybe bringing the y up, y squared as a y to the negative 2. Bring this one up as a y to the negative 4. That makes sense? Okay, so on the side here, let me just rewrite that. My F is actually y to the negative 2 minus 3y to the negative 4. This one I won't have to clean up, will I? The derivative of this is going to be pretty straightforward. Okay, let's get F prime over here while I've got it. What is the derivative of that? So power rule, negative 2 comes out. Y to the negative 3. And then the negative 4 comes out, multiplies times the negative 3. You get positive 12. Y to the negative 5. That's what this is going to be. And then we'll write down G, and then we'll write G prime. G prime, we said, was clean. So I think I'm going to go straight to it. Are we okay? All right, so my F prime is negative 2 y to the negative 3 plus 12 y to the negative 5. Then times G, which is just y plus 5y cubed, plus, because of the formula, G prime, in parentheses, G prime. 1 plus 15y squared. Then times F, and I'll write it in the ugly form. Well, I don't know. It depends on which one you think is ugly. If you think that's ugly or that one, or if you think they're both not ugly. Whatever you think. Okay, that would be our raw derivative, right? So did you have any issues with that part? Or yeah, so it's now just a matter of making it look like the back of the book, right? So let me ask you, does the back of the book have any parentheses around anything, or is this all written out? It's all written out. I did what? Yes. So are you telling me to simplify? I'm not sure what you're saying there. Now you just simplify it. Yeah. Yeah. So would you like me to?
No, it's okay, because I don't know, when I'm doing it, I know how to get to the raw derivative. But from then, I kind of get messed up in my algebra,
So you would like me to see? You'd like to see me? Sure, I'll do this one. That's fine. That's why I answer homework questions. So if I was going to do this one, I'm going to multiply this times this. So it's like a FOIL. All right, so let me write that first one down. It would be negative 2y to the negative 3, and I'm multiplying that times what? Y. Okay, let's just talk about just what that would be. That would be negative 2y to what power? Negative 2, because I'm taking y to the first power here, and y to the negative 3, I'm adding the exponents. Negative 3 plus 1 is negative 2. So that would become y to the negative 2. Yes? I've got to do that for all of them. So let me see if I can do the next one faster. This one times this one. So what coefficient will I have? Negative 10. What power of y will I have? Y to the negative 3 times y to the 3. You add negative 3 and 3. You get 0. Y to the 0 is 1. So this is negative 10. Then you do this one. I'll have a plus 12. Y to what power? Negative 5 plus 1 is negative 4. You following? Now we have to go plus. That's this plus. And now the same thing over here. 1 times this. Oh, wait, I forgot one there, didn't I? Okay, I've got to do this one and this one. 60. Y to the negative 2. And then now go to the other one and do the next one. 1 times this. Y to the negative 2. 1 times this. Same thing, right? Negative y to the negative 4. So I've done those two. And now this one. Ooh, what's that? 15, right? Again, the exponents add up to be 0, so y to the 0 is 1. And then the last one, negative 15, y to the negative 2. Yeah, no, that was, I don't know what you're talking about. It was 45 the whole time. I don't know what you're talking about. Maybe I should dim the light since y'all obviously can't see. All right, so now what we do is collect like terms. So like terms are things that have the same variables raised to the same powers. So I have a y to the negative 2 here, another y to the negative 2 term here, another y to the negative 2 term here, another y to the negative 2 term here. So how many of them are there? Let's see, negative 2, 60, that's 58, and 59, and then, so what is it? Is it 14? Y to the negative 2? So you're just adding all the numbers up in front. 14, y to the negative 2. How about the y to the 4th terms? This one here, this one here, it's it, right? So 9 plus 9, y to the negative 4. And then finally, plus 5. Now, I doubt that's the back of the book. Is that the back of the book? They put all the y's on the bottom. So they put 14 over y squared plus 9 over y to the 4th plus 5. Is that the back of the book? They put the 5 in front. That's fine. Yeah. So that's the back of the book? Okay. See it? So one could argue that the calculus isn't really the issue as much as the algebra simplification becomes the issue. And I would agree. Man. If I tell you yes, then the rest of the department math faculty will get mad at me. Yeah, you know? They get mad because the issue that we have is that students are still like getting through Cal 1 and they still can't do algebra. And the only way to force you to do algebra is to tell you to clean this thing up. So I would say when I'm grading a test, if it's a quiz in class, I just want to see the raw derivative because we don't have time normally to simplify. But on an exam, you should be prepared to simplify it as much as you can, you know. But I will look for the raw derivative. That'll be a majority of the credit. Can you take the derivative? Now, the algebra after that, you know, it'll be worth something, but it won't be everything. All right. Anything else on the homework? 16. T minus root t over t to the 1/3. G of t. That's what you wanted, right? Derivative of this. So do you see one of our rules here? Yeah. Which rule? Quotient rule, right? We're in quotient rule. Tell me, you're grading a student's paper, okay? Here's what they wrote. Tell me what you're thinking. Watch, this is what they wrote. Okay, this problem's worth 10 points. So how many points should this student get for the raw derivative here? 0? Wow, you're a harsh grader. They took some derivatives correctly, right? But they did not apply the quotient rule, right? All they did is took the derivative here, derivative there, and boxed it up. Well, they didn't box it now. They boxed it up, and they went on, right? It's completely incorrect. So don't make that mistake, right? You have to recognize the quotient rule. The quotient rule, on the top we have some function f, on the bottom we have some function g. The derivative of that then should be f prime g minus g prime f all over g squared. Did anybody go to get help with the tutor or anything like that, and now they're using the other formula? No? Not yet? Hasn't happened? Okay. So y'all are sticking with that one so far? Okay. All right, so can you find the derivative of f? Are you going to be able to give me the derivative of this up here? Yes, because it's just two different terms, right? You do them one by one. That you can do. Derivative of t you got. Derivative square root t you should have. Derivative of g, well, that's just a power rule on that. We should be okay. So I don't think there's anything I need to do necessarily on the side. Scratch work, I hope we're okay. This is equal to, let's go with f prime. Starting with this right here, f prime. Tell me derivative of f. 1 minus 1 over 2 root t. So derivative of t is 1 minus derivative of the square root of t is 1 over 2 root t. Just like derivative of square root of x is 1 over 2 root x. Okay, that's f prime now times g, so t to the 1/3. Don't need it in parentheses because there's only one thing, so you don't have to put it in parentheses. You could, yes, it wouldn't be incorrect. This has to be in parentheses because there's two terms. Okay, minus, what's g prime? 1/3 t to the negative 2/3. I don't need that in parentheses either because it's one term. But then times f, so f is t minus root t. All of this divided by t to the 1/3 squared. And now we could go play the same game we just played with all the exponent properties and stuff and clean this up. I'll clean it up. You don't want to clean it up? I'll clean it up. If I'm going to clean it up, though, you got to give me at least one more line where I can kind of simplify some things here. And you can tell me what I'm doing after I'm done, or what I've done. What have I done here? Yeah, I brought this thing, t, this is t to the 1/2, and I brought it up as t to the negative 1/2. Over here, I rewrote this square root t as t to the 1/2. Here, when you have something to a power, all of that to a power, you multiply these two. 1/3 times 2 is 2/3. So what I'm doing is I'm getting everything in rational exponents so that I can start using the properties of exponents to add exponents together when I multiply. And now I'm going to do some distribution. I'm going to distribute this here, distribute that there. I'm going to take this whole thing and distribute it here and here. So let's try this first one. T to the 1/3, distribute through to a 1. You just get T to the 3rd. T to the 3rd, 1/3 times all of this. Negative 1/2 still there? Yes? What power of T do I have? So I have to add these two together, right? Negative 1/2 plus a 1/3. Yes? So that's where you break out your old fraction skills. Negative 1/2 plus a 1/3. You have to get a common denominator. Right, 6. So you rewrite the first one as negative 3/6 plus what? 2/6. And then you add those up and you get negative 1/6. So putting these together, we should get negative 1/6 as our power. We're done distributing through. Now I'm going to distribute this whole thing through, including the negative. I'm going to go ahead and bring the negative with me. Here and then here. So let's do the first one. This times t. Remember, that's t to the first power, right? So I'll have negative 1/3 t to 1/3, because you're going to do negative 2/3 plus 1, which is going to give you 1/3. And then I do negative 1/3 times negative, that's going to give me positive 1/3 t to the, so you have to do negative 2/3 plus a half. What is it? Negative 1/6. Okay. Just telling you where that came from. This. Are we done up top? Everything done up top? Yes? All of this over t to the 2/3. And now what? Split it up into 1, 2, 3, 4. Oh, wait, we do have like terms up there. Yeah, we can put those together first. So what's 1 t to the 1/3 take away a 1/3 t to the 1/3? 2/3 t to the 1/3. So I have 2/3 t to the 1/3. That's these two together right here. And then I have this right here can be put together with this right here. So what is negative 1/2 of these plus a 1/3 of those? Negative 1/6 of those. So I have negative, what is it? What? Is that right? Negative 1/6? That was it right there. I'm doing negative 1/2 plus a 1/3, right? Yeah. Isn't that what we did right here? Yeah. So negative 1/6. Check it again. Find it? Okay. So what now? All over, okay, so all over t to the 2/3. And now I have this over this, this over this. Split it into two fractions. So I have 2/3 t to the 1/3 over t to the 2/3. Then I have, I'll put the minus in the middle of these, 1/6 t to the negative 1/6 over t to the 2/3. How do you do these when you have division with these powers? Subtract. So I need to do 1/3, take away 2/3, which is negative 1/3. So I'm almost there. I have the 2/3 that were up there. When I do the property of exponents, I get negative 1/3 here for these two together. And then here, negative 1/6, take away 2/3, right? Subtract 2/3. That's negative 5/6. This is like an exercise in fractions, right? So minus 1/6 t to the negative 5/6. Is that the answer in the back of the book, or did they drop them down? Oh, was this an even? This is an even? I feel pretty good about it, but let's just make sure there wasn't a mistake. What chapter is this? 2? 2 what? Number what? Two-thirds t to the negative 1/3 minus 1/6 t to the negative 5/6. Got it? Okay. Good. Good questions. These are good exercises. But I think we're ready to move on to today's material. So up to this point, we have established the power rule, which allows us to deal with things to powers, right? Number comes out, subtract 1 from the top. Then we did product rule and quotient rule last class. We realized that that required these formulas that weren't very natural, right? And then we come to today, which is the almighty chain rule. So chain rule. We're going to spend the whole day on chain rule. There are different approaches to teaching the chain rule, all right? I'm going to give you 2. I'm going to give you 2 approaches of the 3. And the 2 that I'm doing are the ones that I think are easier to follow. We'll see. So let's just recall some notation. When we've said, like, y is a function of x, then when I say y prime, that meant the derivative of that function, right? Yes? But there was another notation, dy dx, which means exactly the same thing. And the importance of this notation is that it gives you a little bit more information than this notation does. This notation just says, hey, take the derivative of y, right? Or what's the derivative of y? This one says, what's the derivative of y where x is the variable? This one right here assumes that everyone understands that x is the variable. Understand? Just in terms of, if you walk in this room and I just write on the board y prime, that's a derivative of y, but it doesn't specify what the variable was. Like the problem we were just doing, the variable was t, wasn't it? This doesn't show you that there's a t in there. If I wrote it with this notation, I would have to have written dy dt, and then you would know that t is the variable. Make sense? Yeah? Okay, so that's just a notation thing. So let's talk about our first example and try and recognize the difference between this and what we've seen before. So I'm going to start with an example. Y is sine of 10x. I want to know what the derivative of that is. So your instinct might be, well, cosine of 10x, right? Because the derivative of sine is cosine, yes? And that might be your instinct, and partially you are correct. But the problem is the formula for the derivative of sine of x assumes that the only thing that was inside here was x. It does not tell you what happens if that's 10x. And so what we have is the sine being composed with another function. This is composition. It is a function, 10x, inside of another function, sine x. Do you all agree with that? Yes? So then, to find the derivative, how are we going to handle it? So that's where the chain rule comes in, all right? So the way we want to visualize this first problem is that we have an inner function and an outer function. It's like an onion layer, right? What is the inner function? And the inner function is order of operations. Do you remember talking about this in the very beginning? This was like on a quiz where you had to I gave you a function. You had to come up with a composition of 3 different things, like f, g, and h, that makes this bigger. The same thing. I want to know what's the inside function here. 10x, right? What's the outside function? Sine x, right? Yes? All right, so we have like 2 layers to this onion. The way that we do chain rule is that we attack each layer of the onion starting from the outside in. So here we go. Ready? What we want is dy dx. Everyone agree? That's what I'd like to find. I'm changing notation on purpose here. Even though I said here find y prime, we know that that's the same thing as this. Now what I'm going to do is I am going to decompose this function y as follows. Starting from the outside, and I would write this exactly the way I write this if this is your first time ever seeing chain rule. Y is equal to the outside function first, which we said was sine. It's sine of something, right? 10x, but who cares? It's sine of something. Let's call that something inside there, I don't know, why don't we call it u? Do you agree that y is sine of u? Well, yes, as long as u is what? 10x, right? So on my next line, underneath this, I'm going to write, well, u then has to be 10x in order for that to be true. Does that logically make sense to you? Y is sine of u as long as u is 10x. Okay, now I'm going to construct out of this a table. And on the right side of the table, I'm going to take derivatives. The first one I take is I'm going to look at this right here, and I'm going to find the derivative of this. So I'm going to be finding the derivative of y. But what's the variable in this problem? U, yes? So I'm saying what's the derivative of y with respect to u? dy du, what is it? Well, what's the derivative of sine u? Cosine u, yes? That makes sense? Now we move to the next part of the table. I have u is equal to 10x. I'd like to take the derivative. So x is the variable here, right? So I'm going to write du dx. You follow? What's du dx? What's the derivative of u, treating x like the variable? So what's the derivative of 10x? 10. Okay. We're done with the actual derivative part of the problem. The question is, how do we use this table to come up with our answer? Well, dy dx is what we wanted, right? I have dy du. That's not what I want, though. I have du dx. That's not what I want. So here's what the chain rule says. Do you agree that this is the same as dy du times du dx. Does it make sense logically that these are the same? Why? Basically, these du's cancel, and you have dy dx, don't you? But if you don't cancel them and leave them there, almost like a hidden one, then the dy dx can be written this way, couldn't it? And so what is dy du? This. What is du dx? This. So let's write those down. This should be equal to what? Cosine u times 10. Any questions? I'm not done, but any questions? Yeah, I could have used anything I wanted. Well, I would have stayed away from x. Yes, but anything else? Use a standard one, though. U, V, W. Those are usually the ones we use. All right, so what I'm saying is, I mean, this should be the answer according to the chain rule. It should be this. The problem is that our answer has u in it. And I came up with u, right? Like, we just sat there and said, we're just going to call this thing u out of nowhere. My answer cannot have u in it. It has to have x in it. So all I need to do is go back to my table and figure out what was u. What was u? 10x, right? So let's just rewrite this answer again, replacing the 10x, the u with 10x. Also keeping in mind that this u is trapped in the cosine, right? This 10 is being multiplied. You cannot force numbers in through cosines, right? So this 10 is like a constant sitting on the outside. So since it is a constant on the outside, how about if I just write it out in front? 10 cosine 10x. Questions? That's the answer. Oh, there's a shorter way, but in my experience of teaching it, when I try and do the shorter way, the sharp students will get it. But the students that aren't there, they get blown away. And so this table format is the safe way to present it for the first time. It should get everybody in the same place. Now, I told you I was going to show you two ways, right? Now I show you the fast way. Because if you go and you pick up a Cal 2 student right now and pull them in from the outside or her out from out there in the hallway and say, hey, what's the derivative of sine 10x? They sure as hell won't need a piece of paper. Okay, they'll do it all in their head. All right, so let's see how it's done. It's pretty, I don't want to say it's easy. Because if it were easy, then that's what I would show you, but some people just don't pick it up. Maybe for this example, you will. All right, so for this, I'm going to start the problem over. Now the short way. Y is equal to sine 10x. And I'm going to move it down so I can get up on the board. There's no way I can do this really easily with the video that it's going to make sense for someone to watch it again, but I don't really care. All right, so when I'm looking at this, all right, I still see the onion. I still see two layers. See an outer function and an inner function. So what I do is I start with the outer function, and I cover up what's inside of it. Just act like it's just a blob of something. So sine of my fist. Right? That's sine of my fist. What is the derivative of the sine of my fist? Cosine of my fist, right? So what I'm going to do is I'm going to say that the derivative of this should be cosine of my fist. What was my fist, though? 10x. Okay. Then chain rule now says times, this is the important thing, times, I have exhausted the sign, right? I have already taken care of the outer layer. So now I'm allowed to go into the next layer and look at that and take the derivative of that and tack it on to the end. So what's the derivative of 10x? 10. So I put it out there and I'm done. like I said, this is the first example, though. Okay, let's keep that in mind. This is the first example. So, you know, you want to get to the point where you can do these mentally, but there are problems that are complicated enough that you can't do them mentally, and you have to have a process. All right, so same sort of thing. We're done? Let's do another example. Y'all like that way? All right, here's a new example. Y is equal to sine to 10th, no, x. There we go. So I put that 10 in a different place, didn't I? This is not a product rule. This is not a quotient rule, right? There's no product there. I mean, I guess you could say it's sine times sine times sine times sine 10 times, but wouldn't want to touch that. So, do you see it's a function inside of a function? And maybe this will help. We got to make sure we are clear with notation. When you write that, what we really mean is this, right? When you write sine to the 10th power of x, what we mean is you do sine of x and then raise that to the 10th power. It's purely a notation thing. I don't know who started it, but it's wound up confusing too many people. This right here is equivalent to this, right? So if you're looking at this as an onion, what's the outer layer? 10th power, right? Something being raised to the 10th power. What's the inner layer? The sine x. So maybe we should try this the short way first. Short way first. Okay, so I said if you're going to do it the short way, you have to start with the outer first, right? So now I'm going to bring some props in here. I have sitting here a keyboard to the 10th power. What is the derivative of a keyboard raised to the 10th power? 10 keyboards raised to the 9th power, right? But what's the keyboard? Sine x, right? So I'm going to write 10 of those keyboards, which was sine x, raised to the 9th power. And that would be the outer layer, wouldn't it? Times, now you're free to go inside to the next layer, which is the sine x, and take its derivative and tack it on. So what's the derivative of sine? Or what was the derivative of the keyboard? The keyboard was sine, right? It is cosine x. And you are done. Now the longer way would be to do this. That's done. The longer way would be to write y as being the outer function. What was the outer function? 10th power. So it's raising things to the 10th power. What's the thing that's being raised? Sine x. And then you make your table. What do I write right here? D y d u would be 10u to the 9th. What would this one be? Du dx would be cosine x. So y prime up here really means dy dx, which is just du dx, I'm sorry, dy du times du dx. You're basically taking these two things and multiplying them together. So this gives you 10u to the 9th times cosine x. But what's u? What's u? Sine x. So this becomes 10 sine x to the ninth. Whoa. Wow, what was that? Sine x to the ninth cosine x. My pen doesn't like doing it the long way, so it starts doing weird errors and stuff. Could I have written this answer this way? Yeah? Yes? That would be okay up here? Yes, that's correct also. Questions? Chain rule seem okay so far? So far. We did a problem last class. See if I can bring it up real quick. There, that one. Remember that one? This was an example I gave you last class where it was, we had to apply the product rule twice. Do you remember that? Like within the product rule, we had a product rule. Okay, I'd like to address that now. Now that we have the chain rule, I'd like for us to address it. We'll see it's much easier now. All right, so let's find the derivative here. Shortcut, yes? I don't even want to call it a shortcut. I mean, it's the way most people take derivatives after they've trained their brains enough with this. They just do it visually. So I've got outer function is what? It's cubed, right? The cubing function, it's cubing something, and then the inner function is just x squared plus 1. So I can look at this 2 layers. So I start out with the outer one. So that is, I'm running out of props. Got some glasses. These are inexpensive glasses because I lose them all the time. These are glasses cubed, all right? Derivative of that is 3 glasses squared. But you have to just remember what the glasses are, right? The glasses were the x squared plus 1. Then squared there, right? Chain rule says now, you're not done, times the derivative of what was in there, derivative of the glasses, which is just 2x. And that gave us, you can move the 2x to the front with the 3, and you get 6x times x squared plus 1 squared. And we're done. It'd be a good day to have the clickers, because I really would like to know how many of you would prefer the shortcut. But I don't want to make people feel awkward either. So how many of you so far are like crystal clear with the shortcut? Yeah? Yeah? Okay, that's a majority. Let's see how long we can last with the shortcut, all right? But just remember the other way is always there, all right? And I might have to show you one, we'll see. Up to this point, the onions that we've done have only been 2 layered onions, and we know that onions have more than 2 layers, right? So, what's that? Like ogres, yeah. Oh, don't make me cry. So let's do something a little more complicated. You've been thinking Shrek this whole time anyway? Yeah, me too. It's a good movie. No, I won't do that to you. So now what we need to do is determine what we have here. Product rule, quotient rule, chain rule, power rule. What do we have? Just chain. Be careful. It's not all the above. I'm only saying because we are going to have problems in a little while. They're going to have chain rule. Within the chain rule, there's quotient rule. Within that quotient rule might be a product rule. They get really elaborate, possibly. So we don't, this is just composition. That's all this is. So a way to think about it is if you are X, right, the first thing that's going to happen is you're going to do 3x plus 1, which is a little linear expression, right? 3x plus 1. That's all by itself. After that happens, what? Square root of that. After that, tangent. After that, square root again. So now let's go backwards. The last thing, the outer layer of the onion is what? Square root, inside, 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 linear function, right? So this layer, this onion has 1, 2, 3, 4 layers to it. So let's see if the shortcut will, if you can handle the shortcut at this point, because it may not be, it may be too much. I think this is a good one for the keyboard. Ultimately, I have the outer one is the square root of the keyboard. So what are we going to have here? 1 over 2 square roots of the keyboard. 1 over 2 root 1 over 2 root keyboard, keeping in mind what the keyboard just was. So 1 over 2 square roots of the keyboard. The keyboard was everything in here, right? That was the keyboard. So tan of the square root of 3x plus 1. Agreed? Okay, we have now done the outer layer of the onion. So we go into the next layer. So I don't know how you want to do this. You know, maybe just say, I'm done with that part. So now I'm looking at tangent of the square root of 3x plus 1. So keyboard's not going to work for that one. I think this mouse pad will work just fine, though. So I have tangent of the mouse. What is this called? Mouse pad. Tangent of the mouse pad. Tangent of the mouse pad. The derivative of tangent of a mouse pad is what? Secant squared of a mouse pad. And that's going to be added, multiplied. Chain rule is always multiplication. So we have secant squared of the mouse pad. And the mouse pad was everything in there, right? So that should be my square root 3x plus 1. Times, because I'm not done. Time to go inside. I have now exhausted the tangent. And so I go inside. What's the next function? Square root of, I've got something right here. No, I've got a remote control that looks like it's going to fit just perfect in there. Square root of a remote control is, what's the derivative of that? 1 over 2 square roots of the remote control. So 1 over 2, whatever you want, man, I don't care. 1 over 2 square roots of the remote. What was the remote? 3x plus 1. So that remote was just the 3x plus 1 right there. Times, we finally made it to the linear function. The derivative of 3x plus 1 is 3. Done. Now, we'd have to clean it up. Nah, forget that. Leave that for someone else. But you would want to at least put it all into one fraction. So let's get the numerators together here. This is in the numerator, and there's a 3 up there. So I could put like 3 secant squared square root 3x plus 1 all over 4 square root tan of the square root of 3x plus 1. Then I had another square root over there, right? This one over here? That's really, that's on the bottom, isn't it? So I can just tack it on like this times, here's another square root. 3x plus 1. That's good. Yes, those 2's were both in the denominator, so 2 and 2 became the 4. You could. I mean, with a computer. Mm-hmm. Absolutely, but there are huge domain restrictions on this thing. We got major domain restrictions. I just made this function up, just, you know. This is only defined if 3x plus 1 is greater than 0, greater than or equal to 0, because square root wouldn't be defined. But then you got to make sure that what's coming out of the tangent function is also greater than or equal to 0. So the graph of this would look crazy because the domain is all messy. Am I making sense at all? Yeah, okay. Yeah. And then derivative of that would be the slope of the tangent line wherever it exists. All right. Y'all like the shortcut? Do y'all want to see that one with the long way, or yes or no? No? Why don't I just do just this one? This will be the last one I do long, okay? Y is equal to the square root of tangent of, I didn't need the parentheses, square root of 3x plus 1. All right, here we go. Y is equal to the square root of something, right? U? But that U, that was the keyboard, is actually tangent of something, right? That was the mouse pad, which I'll call W. But W is the square root of something, which I will call M. And then M is what? 3x plus 1. Now, see, this may seem even more complicated to you now, right? You're saying, y is the square root of something. Okay, here's the something. We're calling this U. U then is tangent of something, so I'm calling it tangent of W. So this is W. But W is the square root of something, but that's something I'm calling M, and that M is 3x plus 1. And now you can create a table, and you will have how many derivatives here? 4 of them, right? What's that first one going to be? D, this is important, D, y, d, u, and what's the derivative of y with respect to u? 1 over 2 root u. And then du, dw, which is secant squared w. Then dw dm, which would be 1 over 2 root m. And then dm dx, which would be 3. That all makes sense? Our answer is this times this times this times this, written all out. So y prime, or dy dx, will be 1 over 2 root u times secant squared of w times 1 over 2 root m times 3. And what? Now backfill everything now, right? What was m? Well, m was 3x plus 1, so that gets replaced with 3x plus 1. What was w? Square root of m, but what was m? 3x plus 1, so it's square root of 3x plus 1 goes right here. What was u? Tangent w, but what was w? Square root m. What was m? 3x plus 1. So it's like you have to do all this backfilling, and it's kind of a pain in the ass, but you would get back to what we had before. Is that good enough to show you that? Yeah, but you know, I feel like I don't want to leave you with nothing to fall back on if you need it. Let me see here. Y is equal to x squared plus 1 squared over x cubed minus x minus 4 cubed. That's a rational function. Polynomial divided by a polynomial. I would like to find the derivative, please. So this is the first time we've had this. What do you see? Tell me what you see. Quotient rule. Good. But we have a little bit of an issue. Because if we're calling the top f and the bottom g, right, we know the derivative of this is going to be f prime g minus g prime f all over g squared, yeah? But we got a little bit of an issue with f prime, don't we? F up here is an onion, right? It's composition, right? So when I take the derivative of f, I'm going to have to apply the chain rule to that piece, yeah? And then I'll write down what g is, and then I'll say minus, then I go to g prime, and I notice that g is also a different onion, and I will have to apply the chain rule to that onion. Do you see that? Yes? Do what? Okay. If I just wrote this problem down by itself, forget everything else is there, that you would do doing chain rule, right? Well, we have to, in the quotient rule, we have to find the derivative of that top by itself. And then within the quotient rule, we have to do the derivative of the bottom by itself. So this is a quotient rule problem with two chain rules inside of it. Do you see it? Two quotients, product that creates two quotients. Forget it. It's a quotient rule that creates two chain rules. Well, we have to work it out. So, all right, so what I'll do is on the side here, I'm going to write down what f is. Right? And because I'm going to need this formula, I'm going to need its derivative, right? So let's do its derivative. Let's see if you're really okay with the substitution, the short way of chain rule. What's the derivative of that? Give it to me, don't give it to me simplified. Give it to me like as you do it. I'm going to write it down like as you're doing it. So 2 times x squared plus 1 to the first power times 2x. Okay, if you got that, you're good to go with that right there. Okay, that is the chain rule on this one. So it's my mouse pointer raised to the second power. So it's 2 mouse pointers to the first power. Then I go inside and I take derivative of the mouse pointer, which was derivative of this, which is 2x. That's just what f prime is now. Let me clean it up. 4x times x squared plus 1. Okay, I'm going to have to do something similar for g. So let's write down what g is. G is x cubed minus x minus 4 cubed. And that means the derivative of this will be 3 times the inside x cubed minus x minus 4 squared times 3x squared minus 1. Parentheses. Have to be here. They have to be here. I will take off on the test if they're not there. If this is two terms, Why, then it gets a parentheses. If it's one term like it was up here, you don't need parentheses. Because, this is just going to move out here in front. There's no big deal. Here, this means that 3 would have to distribute to both of those. And we can't mess with this because it's being squared, so it's just going to stay there. So I could write maybe this. 3 times 3x squared minus 1 times x cubed minus x minus 4 squared. That's G prime. Questions, comments, concerns, gripes? You couldn't do this into here until after you squared this, which I don't think any of us feel like squaring that right now, right? So we're just going to leave it like this. All right, are you ready to put the answer together? It's going to look real bad, but it's going to be this right here. So make sure you have plenty of room. Y prime equals F prime, which is this right here. So 4x times x squared plus 1 times G, not G prime, right? Times G, which is here. X cubed minus x minus 4 cubed minus G prime, which is the bottom right corner there, 3 times 3x squared minus 1 times x cubed minus x minus 4 squared times f, which is x squared plus 1 quantity squared. Oh my. Oh my. All over G squared. X cubed minus x minus 4 cubed, but then squared, so 6th power. Is this okay, though? I want to make sure everyone's on the same page. Two and the 3. Oh, yes. The power, the exponents, yes. When they're the same base. X to the n times x to the m is x to the n plus m. X to the n to the m is x to the n m. Ooh. So we had something to a power, all of that to a power, we multiply the 2. All right, now, believe it or not, if you remember correctly, this derivative was graphically the slope of a tangent line. And we are interested later on in figuring out where the slope of tangent line is 0, right? Because we want to find like highest points on a curve, lowest points on a curve. So we want to be able to take that and set it equal to 0, which looks like a catastrophe, doesn't it? So I'm not going to say set it to equal to 0 now, but what I want to show you is something that we could do if we were headed that direction. And that's look at the numerator right now and see if you can factor it. See if there's a greatest common factor. So let's take a look at numbers. 4 here, 3 here. Nothing in common, right? I have an x here. Do I have an x by itself here anywhere? No. I have an x squared plus 1 factor. Do I have an x squared plus 1 factor here? Yes, I do. I have 2 of them, right? 2 factors. So couldn't I pull 1 factor out? Watch what I mean by that. I could pull an x squared plus 1 out by itself. Just one of them. Then how many of these do I have? I have 3 factors here, and I have 2 factors here, so I can pull 2 factors out. Anything else that I can pull out of both of these? No? All right, so now I'd put maybe a big bracket so you can kind of see What would be left if I pulled this out and this out? What's left here? 4x and one of these factors, right? So it'd be 4x and one of those factors. All right, what would be left here if I had pulled out this, right, and this? So negative 3 is still there. Then x squared minus 1. Then x, I did forget the 3x squared. And we pulled both of these out, right? So it's gone. And then we pulled one of those out, so just x squared plus 1. That's all that would be left in there, right? All of this over x cubed minus x minus 4 to the 6th. Anybody see anything we can do here? Cancel a couple of factors here. This is x cubed minus x minus 4 to the 2nd power. And here we have 6 of them. So I could actually cancel out 2 powers and make this a 4th power instead, couldn't I? Anything else we could do? What's going to happen later is that we are going to be able to multiply this all through and clean this up. And this is going to be something that we'll investigate further. So I may as well go the rest of the way. I'm going to go here like that. I'm going to go here, 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 and then I'll distribute a negative 3 through. So here's where I am. Algebra on steroids, I promised. I promised, and I'm delivering on that promise. Okay, so multiplying through 4x times x cubed is 4x to the 4th, then minus 4x squared, then minus 16x. Then I multiply here 3x squared times x squared is 3x to the 4th times negative 3, negative 9x to the 4th. 3x squared times 1 is 3x squared, but then times negative 3, so negative 9x squared. And then negative 1 times x squared is a negative x squared, but then times 3, so negative 3x squared. And then finally negative 1, then times negative 3, which would be positive 1. Is it positive 3x squared? Yes. This would, I forgot to do the negative. So negative, this positive 3 at the end. I got rid of the brackets because the brackets were just to help you see that this stuff got factored out of everything. Really, at the end of the day, it's just a set of parentheses. And now I can collect like terms, right? I'm done, though. I'm exhausted from that problem already, so I'm done. To the 4th. So put it together and we're done. That's simplified. That's simplified now. Yep. Any questions? Four x squared. What are you saying? No. We're putting like this one and this one together. So that gives us negative 5x to the 4th. Then these two and that one can go together. So how many is that? Negative 10 x squared. And then what else? Minus 16x and then plus 3. That's what the inside of that cleans up to be. This. So what we have is the final answer would be x squared plus 1 times this over x cubed minus x minus 4 to the 4th power. All right, awesome. All right, we have, I want to give you one more example that I wanted you to work on problems in class. The thing about chain rule is the only way to get really good at it is to just start doing it. And I can show you a bunch of examples, but then I can give you another 100 examples that are completely different. So it's just understanding the concept. Let me see if you can handle this one. No, this is my problem that I'm going to do, and then I'm going to give you all some problems to work on. I want you all to start your homework. You know what? Can we change this sign to a secant? Thank you. Appreciate that. All right, let's try and get our heads around what in the hell's happening here, okay? What are you seeing? You see a power? Yes. What makes you think everyone's down? No, I'm just kidding. I'm just kidding. Go ahead. I'm open to it. Why shouldn't you mix alcohol and calculus? Don't drink and derive or something like that? Yeah. That's right. Yeah. Yes. I have heard that. I mean, obviously I should have heard that at some point in my life, right? Yeah. Okay. Derive is deriving like a formula or something like that. Yeah. Is that how you got your foot? All right. Yes. Yes. Do what? Well, I mean, don't make it look like mine. I mean, you would write this, and then you'd write this, and then. What about that? Yes. This is just simplifying the expression. You need to get good at that. Yeah. I know it looks intimidating, and it is, but, you know, it's just, this is, look, in a problem that's worth 10 points, okay, to me, this is like 6, all right, 6 to 7 points. You want to just barely pass that problem, you just give me the raw derivative. You want the full credit, you want to be an A student, you have to be able to get it down to its simplified form. Practice. Practice. Trying will make you better at it. Okay. Let's talk about this. I heard someone say power. I mean, I see a power. I see a couple of powers. I see a power here. I see a power here. Quotient rule. Okay, so is this overall, is this a quotient rule? Yes? The inside is a quotient, I agree. But we have something on the outside, don't we? Power. Yeah, so that's a chain rule. Look at, that's the keyboard to the -3 power, isn't it? What's the derivative of the keyboard to the -3 power? -3 keyboard to the -4 times the derivative of what's in there. Now your quotient rule comes into play. You see the see that what's happening here? And then that is something you'll have to set up maybe on the side and do. Okay, so let me see if I can work through this with you. Y prime is equal to, I think we said we're all comfortable with this, -3, and then you said it was all that stuff inside, right? Don't touch it, no derivative, just there. To the, you said -4 times. Now, The derivative of what's inside, right? Okay, so watch the way I'm going to write this. Here's the inside. I change colors to stress to you that that's what the chain rule is saying. It's saying it's the outer layer of the onion, right? There it is. There's the derivative of the outer layer times the derivative of what's inside, even if the inside is nasty. So now imagine that that part of the problem is done, and forget that you even have it, and act like that's the problem I gave you to do. Okay? Now, how would you do that problem? Set up a quotient rule, right? F and G. What's going to happen though? The F is easy to take derivative of, right? G is another onion, right? That's something squared. Would you like to try this on your own? Or you want me to take it the whole way? No, oh, be careful. You can't treat this as tangent. Tangent, is that what you said? The derivative of tangent is secant squared. But that's not tangent. No. Okay, so I'm going to keep going here. Does everyone understand what's in red is okay? That's part of our answer. What's in green needs to be figured out still. Because I put the little prime mark on it, meaning I still need its derivative. So I'm going to just draw a line real quick, and I'm going to go act like this is the problem I started with. X squared minus x over secant squared x, right? Write this as f over g. So the derivative of this will be f prime g minus g prime f over g squared. I'm going to write f down on the side. F is x squared plus, or no, minus x. What's its derivative? 2x minus 1, that's nice. And then g, I'm going to write g down. G is secant squared x. The derivative of that is, so this is a little onion, 2 secant x times, now go inside, you've done the squared, right? Derivative of secant x is secant x tangent x. That's it, we're done with this onion, right? Go ask the question, what? How to what? Yes, yes, I will do that. This is 2 secant squared x tangent x. So I have it all, don't I? I have f, I have f prime, I have g prime. I can fill out this entire quotient rule, can't I? In fact, if I want to, I could probably come back up here and squeeze it in right there. Just replace this with whatever this is, right? So let me see if I can get a final answer for us. Negative 3 x squared minus x over secant squared x, all of this to the negative 4 times. All right, so we went inside, took the derivative. It was a quotient rule. The quotient rule was set up here. We had a little bit of chain rule happening in here, right here. So let's write down f prime g minus g prime f over g squared. F prime is 2x minus 1 times g secant squared x. I did not need parentheses. Minus derivative of secant squared x g prime, which was 2 secant squared x tan x, times f, which is x squared minus x. I'll put that in parentheses, all over secant to the 4th. And that is the raw derivative. I mean, you could make these really, really complicated. The book has some good challenging ones towards the end. So I'm going to insist that you look at problems 7 through 41. That's 20 chain rule problems. I recommend that you do them all. In fact, I recommend you do the evens too. There's no such thing as getting too much practice with chain rule. There's no such thing. Page 120. Problems 7 through 41. Well, you know what? You can go to 45. And you should do those odds. And then, always, if you ever finish that, then you go do the evens. Some of these are tough. Let me bring up the solutions real quick. Let me take a look at something here. I can't post these online, and it's because they have the evens, and there's copyright issues with that. I don't have anything where it's just the final answer. Plus, the way they simplify, it would be. Let me see here. I want to see the way they work it out. Let's do this. I said 7 through what? Okay, there's 7 through 15. And then y'all can just go watch the video or something and pause it. See if it comes up clear or not. I don't know if it will, but at least it'll give you some idea of what to do, right? It's kind of tough to with copyright stuff. It's kind of weird because it's educational. It's not profit. It's hard to say this is copyright infringement, unless you're using it to try and make money or you're stealing someone's intellectual property. The reason I don't like to do it is because some instructors like to use even problems on tests. So they don't like other instructors floating the even problems around. That's the thing. Well, instructors know that the students usually don't have the solutions to them. So, you could say, here, I'm going to give you the even problem on a test, and then if the student doesn't get it right, you're like, well, why didn't you try it? If you tried it, you should have gotten it, and if you didn't, you should have asked for help, and whatever. So I don't want to. I'm just looking up something right here. That's all I'm doing right now. I'm just trying to find this one problem. Where is it? I can't find it. I don't know. I'll give up when I get to 45. Oh, yeah, you can do 46 too. No. All right. Well, look, we've got 15 minutes, so why don't we do this? Why don't take a break? I'm going to give you 2 of your own homework problems to work on. If you can get those, you can go. Okay, so I'm going to have you right now do number 21, which is y is equal to x squared plus 1 over x squared minus 1 cubed, and then 23, y equals sine of x cosine x. Okay, 15 minutes is not a grade. I'm not going to, you have to turn it in, but I want everyone working on it. If you get the answer, you come up and show it to me. I would like you to try and simplify 21 as far as you can, but get the raw derivatives for both first. All right? Sound good? All right.